So now we are going to continue working with the previous fruits data set, and instead of having a single hidden layer artificial neural network, now I'm going to use two hidden layers and implement a deep neural network. And before we continue, I'll just a disclaimer warning: this deep neural network, it takes a very long time to train. So if you want to run this code, it's going to take a lot of time. So anyway, we'll start. Import torch, import numpy as np, import matplotlib.pyplot as plt. From torch autograd import variable, and so on. Now we are going to run the same steps as before. I'm not going to describe these steps in a lot of detail because you should have done them by now. The first thing we do is data loading and pre-processing. So we are going to load the data set, the fruits 360 images, and transform into tensors. For that we have from torch vision import datasets transforms. This is the dataset path, datasets image folder. We point to the training folder, and then we transform, calling the function transforms.compose transforms to tensor. So we transform our images to tensor. Then we split the data set into training and testing data set. So we have an 80-20 ratio. We are going to do the same thing again. From torch utils data sampler import random sampler, split 0.8 length of the dataset path. Again, we are going to shuffle, create sampler objects. I'm not going to describe this again in detail, but again, we end up with 6517 samples for training and 1630 for testing. Now we are going to look at the number of classes. So we call the function len dataset train underscore loader dot dataset dot classes, and train underscore loader and test underscore loader are variables that we created here by using torch utils data loader, and we can print the class name. So we have a total of 15 classes that we want to classify. These are the names, and we can show what they look like. And this is the neural network model. Again, our input images, they have a dimension of 100 by 100 by 3. We will flatten them eventually, and we are going to have two hidden layers with 200 neurons each. So this is my deep neural network model. From torch import NN, torch NN functional F. I define the class model, NN module def in itself. NN linear 100 into 100 into 3, the input dimensions 200. NN linear 200 comma 200, two hidden layers with 200 neurons each. NN linear 200 classes number, and these are the number of classes that we want to classify. Forward frelu self fc1, self fc2, self fc3, and log max. So this is what our model is like, and it just differs from the previous one in the sense that we have another hidden layer with 200 neurons. We are going to define the loss function and optimizer. Again, this is SGD for optimization, and this is my loss function. We are going to train the model by carrying out forward propagation, loss computation, back propagation, and updating the parameters. So loss array epochs 50. Again, we are going to iterate over all of them. Over here we carry out flattening by calling the function data.view -1 100 into 100 into 3. We set the gradients to 0 before starting. The forward propagation model out model data. We carry out the loss calculation by comparing the model output with the target variables. We carry out back propagation, and we do weight optimization. So over 50 epochs, so this was the loss in epoch 1, and by the time we got to 49th epoch, after a couple of hours, this was my loss. So we can even visualize it. We don't have to do it, but anyway, we can see that this was the training loss. We can carry out model testing. So we are going to iterate over the test loader. Again, flatten these images and implement the same model on them. and we can run a test loop as before. So even with deep neural networks, we get an accuracy of 100%. So it's the same code as before, but we just have one more hidden layer which we defined over here. So if you work with image data, you can try to adapt the same code, but obviously have one more hidden layer, and we pass it through one more activation function in the same way.